Okay, so we need to talk about the sandwich theorem, or called the squeeze theorem. Basically, it has to do with figuring out if a function is between two other given functions. So I have a picture of some functions, and if you look at the labelings, this one's h of x. H of x is always above f of x, and f of x is always above g of x. So f of x is sandwiched or squeezed between this upper function and a lower function. And so what we're going to look at is if we can figure out what is the limit as x approaches c of g of x, and if that same limit exists for h of x, and I know f of x has to be in between there, then I'm guaranteed that the limit as x approaches c of f of x is that same limit. So that's what we're trying to show here, that okay, here's c, we're looking at the limit of g of x, it would equal c, the limit, or would equal L, I should say, if you go across. The limit of h of x as x approaches c is L, so that's guaranteed then if f of x is in between, that the limit as x approaches c of f of x also has to be L. So once you can guarantee that this function is sandwiched or squeezed in between the other two, and if you can evaluate the limit of those outer functions, and if they equal the same limit, then you're guaranteed that the middle function also has that limit. So that's really what the top of this note sheet says. If I know f of x is between these two functions, and notice it says less than or equal to in any given interval, so it says in an interval about c, around c, then the limit as x approaches c of g of x is equal to the limit of as x approaches c of h of x. If I know that they both equal the same limit, L, then I'm guaranteed that the limit of f of x as x approaches c also has to be L. So that's the premise of what the sandwich theorem is. So what I'm going to want you to do is we're going to start on this sheet. We are going to use the sandwich theorem to prove the limit as x approaches 0 of the sine of x over x is equal to 1. And we're going to use the sandwich theorem to prove that. Now, when you do these proofs, you are not expected to be able to do these on your own. But I'm going to get you started, and I'm going to ask you to pause a few places to try to see what you can come up with, and then kind of look at the rest of the video. So basically, to prove this, here's what we would set up. We'd set up the unit circle. So this is the unit circle with a radius of 1. I'm going to look at 3 different shapes on this unit circle after I draw this angle in. I'll call the angle x, because that's really what we're looking at, is the sine of x. So you can call it theta if you'd rather call it a theta. I'm going to call it x. So this is on the unit circle. I'm going to look at the area of this orange triangle. I'm going to look at the area of the sector, like that piece of the circle. And then I'm going to look at the area of the green triangle. Okay, so I've got the area of the orange triangle, which isn't a right triangle, it's just that the cute triangle there. I'm going to look at the area of the sector, and I'm going to look at the area of that right triangle. This would be a right triangle because that's tangent at that point, so that is a right angle there. All right, so the first thing I want you to do is I want you to take your note sheet. So first draw all of this in on your note sheet, and then I want you to take your note sheet, and on this is the orange triangle, this is the sector, and that's the green triangle. Fill in as many pieces as you can. And I know the area of this has to be smaller than the area of this, which has to be smaller than the area of the green triangle. So I do know these areas are in that order, which is going to kind of help us get to that sandwich theorem to prove the limit as x approaches 0 of the sine of x over x is 1. So I'm going to ask you to pause it right now. Fill in as much of this as you can. Can you figure out the area of this? Can you figure out the area of this? Excuse me, and can you figure out the area of that? So label as many pieces as you can, and then try to see if you can represent the area. Okay, so you should have started to sketch the area of this isosceles triangle. It was isosceles because I knew, remember from this picture, sides were both 1, so it was isosceles. So those sides were 1, this angle was x, and the height of that is just the sine of x. Because again, if you look up here, that's just the y value in the unit circle. It's that point right there, so that's the x, y point, so that's just going to be the sine. The cosine is how many over you go, the sine is how many up you go on the unit circle. So that's just the sine of x. This is 1, x and 1. And then this one I labeled, there's x, that's 1. This side ends up being the tangent of x. Now, how does that happen? Well, remember, the tangent of my angle x is equal to this side over 1. It's opposite over hypotenuse. And since the opposite over adjacent, excuse me. So if the adjacent is 1, then I know that this has to just be the tangent of x. Okay, so there's my labels. So then when I write the equations for the area of a triangle is 1/2 the base, 1 times the height. This is, if it's in radians, you just take the part of the circle you have, which is x divided by pi over 2, that's how much of the circle you have, times the area of a circle, which is pi r squared. And then this is 1/2 the base, which is 1, times the height, which is tangent. So when you simplify all of that, you get sine of x over 2 is less than x over 2 is less than the tangent of x over 2. Okay, so now I need to work with this. This is something I know from my diagram and from looking at my areas has to be true on the unit circle. So now I'm looking at what do I need to get to? I need to get to the sine of x over x. That's what I want in the middle. I want that sandwiched between two other functions. So when I look at this, what can I do to get like the sine of x over x? Well, first of all, I don't like that 2. So I would probably multiply everything by 2. All right? So do that. Multiply everything by 2, and you're going to get the sine of x is less than x, which is less than tangent of x. Okay, so at least we've got rid of the 2's. All right, now I want to get the sine of x over x. So I guess what I would probably do is first, let's get the sine of x in there. So let's divide everything by the sine of x. All right, we can do that. So when I take sine of x divided by sine of x, I get 1. This will become x over the sine of x. And tangent of x divided by the sine of x, remember tangent is sine over cosine, is going to end up being 1 over the cosine. All right, so after I divide everything by the sine of x and simplify it, I get 1 is less than x over the sine of x, which is less than 1 over the cosine of x. Now, when I look at that, I say, well, I don't want x over the sine of x, I want its reciprocal. So all I really need to do then is take the reciprocal of each. As long as I do it to all 3 pieces, I can take the reciprocal of each. So when I do that, reciprocal of 1 is still 1. Take the reciprocal of this, so I get sine of x over x. Reciprocal of this is cosine. Now realize, because you're taking the reciprocal and you're flipping them, you technically also then have to flip the inequality signs. So now I know 1 is greater than this reciprocal, the reciprocal of that, which is greater than the reciprocal of 1 over cosine. Okay, so once I have that, now this function is what I'm looking for. It's sandwiched in between these two. So what I need to do is I need to find the limit of the outside functions. I need to find the limit of the outside functions. So I did that here. It's kind of hard to see, but over here you have to show that. The limit as x approaches 0 of 1. Well, that's a constant, so it's just going to be 1. The limit as x approaches 0 of the cosine of x. I have to show substitution. Cosine of 0, and it's 1. So by substitution, I substitute in the 0, and I get 1. So by the sandwich theorem, since the limit as x approaches 0 of this side is 1, and the limit as x approaches 0 of this side is 1, I know sine of x over x is sandwiched in between there. So by the sandwich theorem, I can say the limit as x approaches 0 of the sine of x over x does equal 1. So we've proven it. So now we can use this in any trig equation. So we can use that as an identity technically, and we don't have to prove it anymore. We just proved it. Again, do you need to make sure you can do this on your own? No, but you do need to make sure, if we get you started. So if we would look at this and we'd show you, okay, we're trying to prove this, we'd give you the setup, we could even give you this and technically get you to, here. If we got you to this point, you should be able to do the algebra so that you can get to sine of x over x sandwiched in between two other functions. Take the limit, show us that. You take the limit of both of these outside functions. If they're the same, then you can state by the sandwich theorem, your limit of your inside function is also that constant limit. Okay? And again, now we can use this in any of your trig limits. You don't have to really show me any work. You can just, anytime you have the limit sine of an angle over itself, as long as you're in radians, because remember we did this in radians, then the answer is 1. If you're in degrees, this formula is going to change right here, because now it's not going to be x over 2 pi, it's going to be x over 360. So that will change there. So if you're in degrees, it would be a lot harder problem, or uglier, I guess, answer to that. All right, so that's the sandwich theorem. I hope that helped.